Hello student. Uh, in our previous lecture we have seen the sequence network of alternator, and you can recall our previous lecture. Unsymmetrical In unsymmetrical fault, the phase voltage and current no more maintain the magnitude is not equal, and they does not maintain 120 degree apart as it is in symmetrical system. Now, according to Fortescue's theorem, any unsymmetrical system can be resolved into three. If it is three-phase system, then three-phase unsymmetrical system can be resolved into two symmetrical system and one co-phasor system. Or in generally we can say, according to Fortescue's theorem, in phase unsymmetrical system can be resolved into n minus 1 symmetrical system and one co-phasor system. Now if we consider three-phase system, then n is equal to 3. In that case, n minus 1 equals to 2. That means two symmetrical system and one co-phasor system. Any unsymmetrical system three-phase unsymmetrical system can be resolved. Now suppose this is VA, this is VB, and this is VC. Now in this case, we cannot say VA is equal to VB is equal to VC. That means we have to measure VA, VB and VC individually. Or we can say according to Fortescue's theorem, VA equals to VA0 plus VA1 plus VA2. And now this VA, it is called zero sequence voltage of FH voltage. It is positive sequence voltage of FS voltage, and it is negative sequence voltage of FH voltage. And similarly, we can say VB, it is equal to VB0 plus VB1 plus VB2, like that. VC is equal to VC0 plus VC1 plus VC2. Now, similarly, it is equally, if it is IA, then if this is, instead of voltage, that is, if it is IA, it is IB, it is IC. In that case, unsymmetrical current can be also resolved like this: IA0 plus IA1 plus IA2, like this. IB, IC, we can. Now, using this Fortescue's theorem, and we have seen the alternator sequential network, and there we see the positive sequence network and zero sequence network and negative sequence network. And also we consider the positive sequence impedance, the impedance which oppose the positive sequence current, that is positive sequence impedance, the impedance which oppose the negative sequence current, that is negative sequence impedance, and similarly the impedance which oppose the zero sequence current, that is zero sequence impedance, and all this one. And one more thing, unsymmetrical fault. Obviously unsymmetrical fault can be considered LG fault unsymmetrical, LLG fault unsymmetrical, and LL fault unsymmetrical fault. All these three is under unsymmetrical fault, and LLLG triple line and ground fault, or LLL fault, it is these two are under symmetrical fault. Though, and in your assignment, uh, some student has written that uh, three-phase involved in fault, they are symmetrical fault, and one or two phase involved in fault, they are asymmetrical fault. Obviously it is true, but at the same time you have to say, if it is symmetrical fault, then the magnitude of the fault current will be equal in each phase, and the angle between the current will maintain 120 degree. Okay, and similarly, if it is for symmetrical fault, if it is unsymmetrical fault, the angle of each phase will no more maintain equal, and the angle is no more 120 degree apart. Okay, now we will see the three cases of alternator fault. One is LG fault, like this, alternator LG fault, alternator LLG fault, and alternator LL fault. By one we will see that. Note it. Now and in our last lecture we have seen that we can find out VA0, VB0, VC, VA1, VA2, it is equals to 1 by 3, 1 alpha alpha square, 1 alpha square alpha, and this is VA, VB, VC. Okay. And as these two are symmetrical system, that means we can say VA1 is equal to VB1 equals to VC1, and similarly we can say VA2 equals to VB2 equals to VC2, and here it is VA0 equals to VB0 is equal to VC0. This is cophasor, that means there is no angle between VA, VB, VC, they are in the same direction, but here VA, VB, VC, they are maintaining 120 degree apart, if it is, and their magnitude is same. If it is VA1, it is VB1, it is equal to VC1, and if it is sequence is opposite, if it is VA2, it will be VC2, here it is VB, here it is VC, and here it is VB2, but here also the angle will be 120 degree, that will maintain. It is cophasor, and that is, these two are symmetrical system. And from here we can find out, and we can say VA0 is equal to 1 by 3 VA1 plus VA0 is equal to VA1, VA plus VB plus VC, and like that VA1, VB2, and VA1 it is equal to 1 by 3 VA plus alpha VB plus alpha square VC, and from VA2 equals is equal to 1 by 3 VA plus alpha square VB plus alpha VC. So VA, VB, VC can be find out. Here one thing kept in mind, VA0 not equals to VA1 or not equals to VA2. VA0, VB0 and VC0 equal, but it is no relation with VA1, VA0, VA2 like that. Similarly, we can say VA1 equals to VB1 equals to VC, but VA1 not equals to VA2 or not equals to VA0. I think you know that. Okay. So take the consider alternator it is neutral point is grounded with Zn with an impedance grounded, and it is Z1 and it is VA, it is equal to VB, Z, you can say this is ZA, this is ZB, and this is ZC, and this is VC. Now, first case 1, LG fault. For LG fault, we assume that alternator A phase is grounded. A phase is grounded, so fault current will flow. Suppose this is IA. In A phase current is IA, and this is IB. It is equals to 0, no current. And we consider the alternator is at and no load condition, and its IC, it is also 0. So only IA will flow, and IA will flow, continue its current in this way. Okay, so IA will pass through, this is IN, neutral current. So IA will be the IN. Okay. Now, from this is IA has some value, IB it is equals to 0, IC it is equals to 0. At the same time, VA, this voltage is equals to 0. This voltage is equals to 0, but VB will maintain a voltage, VC will maintain a voltage. Now, we will see what will happen if this type of fault is occurred, then what will be the different phase voltages condition VA, VB, VC. We know that VA will be 0, and what will be the value of VB and what will be the value of VC. We have to find out it. Okay. And now assume, now we know IA according to Fortescue's theorem, it can be resolved into 3 parts. One is IA0 plus IA1 plus IA2, zero sequence component of IA, positive sequence component of IA, and negative sequence component of IA, and summation of this is IA. Okay, so using this we can say IA0, IA1 and IA2, it is equals to 1/3 of actually from this we have seen this already in our previous lecture, that this is inverse matrix of, from this we will create the matrix, and from that inverse matrix we will get this. Okay, so this is IA and this is IB and this is IC. Now here IA, IB, IC. Now what is IB? IB is equals to 0. So we can put next, we can put IB equals to 0 and also IC is equals to 0. Okay, so IA 0 equals to 1/3 of IE, 1/3 of IA. Similarly, we can say IA1, it is 1/3 of IA. In IA2, it is also 1/3 of IA. Because IA0, IA plus 0, 0, and next, in case of IA1, 1/3 of IA1, then it is 0, then it is 0. So that means from here we can say IA0 equals to IA1 equals to IA2. When all these three currents are equal, now in which case it is possible? This 3 current is equal. That means 3, this is IA0, it is 0 sequence network current, and this is positive sequence network current, and this is negative sequence network current. And now these 3 current are equal. What does it mean? When the current is equal? Current is equal when the circuit are in series. Here that means here the 3 sequential network will be in series. From here it is clearly understood. Agree? Now what will be the positive sequence network? We know that positive sequence, it is A, positive sequence voltage is there, and there will be one positive sequence voltage is there, and positive sequence impedance will be there, and this is the positive sequence network. Positive sequence network, this is positive sequence network. Positive sequence voltage and positive sequence generated EMF, and obviously positive sequence current. What is IA1? Similarly, we know that it is already proved that generator can generate only positive sequence voltage, no negative sequence voltage, and no zero sequence voltage generator produced. Generator produced only, alternator produced only positive sequence voltage. That means here it is positive sequence network. In case of negative sequence network, this EMF EA, it will not be there, because generator only generate negative sequence okay. Let it clearly, we'll draw it here. We'll get a little bit more space. This is ZA1, this is EA, and now this is because this is ZA2, negative sequence, no voltage, so it will not be there, so only it is there. And in case of zero sequence, this we know that this impedance will come in series with the zero sequence impedance. That means if it is ZA0, this is ZA0. Now with this the Zn that will be in series. that will be in series. Here the current IA2, here the current IA0, ZA0, IA0, and this is Zn. Now this is Zn, and one thing here it is IA0, it is through In, what is passing? That means Ia is passing through In, and In is passing through Zn. In is passing through Zn, and Ia, it is equal to Ia0, and it is equals to Ia is equal to Ia0, and here it is Ia0 1 by Ia, or we can say Ia0, it is equal to same as, the magnitude is same as, so we can put it here Ia0, or we can say this Ia, it is 3 Ia0, and Ia it is passing through In, or we can say In is equal to 3 Ia0. That means through Zn, how much current is passing? 3 Ia0. And through zero sequence impedance, how much current is passing? Zero sequence impedance, that means current is zero sequence. Now how can it be possible? It is a series network. Through this impedance here, through Zn it is passing In, it is equals to In, and In equals to 3 Ia0, and here it is Ia0, it can be possible. And also in that case, what we can say it is Ia0, and also these two are in series, that means same current will pass through, so if we say it is Ia is passing through, that means these 3 will come here, so instead of Zn it will be 3Zn, so zero sequence, so actually Z0, total zero sequence impedance here, it is equal to ZA0 plus zero sequence impedance of this phase is equal to ZA0 plus 3 of Zn. Actually zero sequence impedance. Okay. And here it is, we can say it is Z1, and here it is Z2, we can say it is Z2. Positive sequence impedance, it is negative sequence impedance, it is positive sequence impedance, and these two in series will act as a zero sequence impedance. Okay, now so how much current here? Through here it is passing Ia1, through here it is passing Ia1, and here it is passing how much? It is Ia0, Ia2, Ia1, and here it is passing Ia0 equals to Ia1 equals to Ia2, and here is voltage is how much? This voltage is how much voltage? Zero sequence voltage and zero sequence impedance. So sorry, zero sequence current product zero sequence impedance, that means VA0. What is this? This voltage is VA2, positive sequence voltage. This is zero sequence voltage, this is positive sequence voltage. Sorry, this is VA2, 2 means negative sequence voltage. This is 0, that means zero sequence voltage. and here it is VA1. VA1, that means here it is show VA1, VA2, VA0. What is this? So that means this is VA voltage of VA phase voltage, and it is equals to how much? It is equals to 0. So this is the three sequential network of this circuit. Okay, so these three are the three sequential network of the circuit. Now if from here IA VA1 is how much? VA1 it is equals to EA minus I1 IA1 Z1 or ZA1, what is, and VA2 it is equals to IA2 minus IA2, EA it is equals to 0, so we can say 0 minus IA2 Z2, that means IA2 ZA. And now VA0 it is equal to minus IA0, IA2 it is IA0 into Z0. So Z0 is equal to, put this ZA0 plus 3 of Zn. This is zero sequence impedance and this is neutral impedance, neutral grounding impedance. Okay, so from here we will get the voltage and from here we will get the current. So from here we will get the sequential voltage. So if we know the VA, then we can say we know the VB, we can know the VC. Similarly, we know the V0. VA1 is known, that means VB will be, VB1 will be known and VC will be known. VA2 is known, that means VB2 will be known, VC2 will be known, and VA2 is known, that means VA0 is known, that means VB0 and VC0 will be known. And once the VB0, VB1 and VC, once this VB1, VB2 and VB0 is known, then take VB is equal to summation of these three. Okay, so by this is the derivation for LG fault, sequential network for LG fault. This is sequential network, sequence network of LG fault, and this is sequence current, and this is sequence voltage. Okay, so take a snap.